Okay, now it's being recorded. So let me, although I said that I will not talk about the experiments which led us to this theory and why they forced us to this theory and why it seems like there was no other alternative, but still just as an invitation, I'll tell you what kind of problem there was so that you have some idea that what we are talking about and how strange the physical reality is as purported by quantum mechanics. So first of all, what is the scope of this theory? What is the scope of quantum mechanics? My this pen today is a little bit broken, so my writing today would be a little bit sloppy, but I'll change it before the next class. So the scope is, by scope I mean that what does it apply to? Well, it applies to everything. It is the rules that govern the world. It is the framework that governs all theories of physics or nature. So it's not a particular theory. It's just a framework in which you have to devise your theory. And it is quite different from classical mechanics. So how is it different? As a framework. So in classical mechanics, you assume that what you have, you idealize things. So for example, you want to follow the motion of some object. That object may be extended, but then you can divide it into small parts. And you can say that I'm gonna idealize some point particles in that object. And so for example, if I have a table, I can just consider, even if I don't have an idea about atoms, I can just think that I'm concentrating on each small part of this table. So these are like points, and I'm following that points. Or it could be just particle, a small bead or a small marble whose motion you are following. So you assume that you have particles. World is made of particles. Made of particles. You don't have to assume atoms. It's just that you can follow the motions of objects by concentrating on their small parts. So assume that you have particles, and these particles have some position x at different times t, and the whole game is you want to give a differential equation. You want to give a law. There's a continuous change in the position of your particles which are there in your system, and you want to give a law for that. And what kind of law you're going to give? You're going to give a differential equation. Because this differential equation will have solutions, and given some initial condition, it will tell you where the particle is at any given time. And I'm not assuming anything like what kind of law I should give. I'm not even assuming that it should be Newton's second law. I'm not even saying what order of differential equation should it be. It's just the very basic which you think you should be doing. We know that in the end, we want second order differential equations. But this is even more basic. This is what you think you are doing in classical mechanics. So it's like the whole game is guessing the differential equation. Now, it turns out that now you may think that when I go to quantum mechanics, I was given some kind of a differential equation. So for example, for gravity, for particle moving in an electric field, and I want to change the differential equation. Maybe the differential equation becomes very complicated. Some kind of a partial differential higher order equation. No, that's not what you're doing. This whole idea that you have a position for a particle at any time, and whose evolution with time you are finding through solutions of differential equations, this has to be thrown out. That's not what we will be doing. Then there are other things. Well, at least not, this is not exactly what we will be doing. Maybe something close, but not exactly this. Then in classical mechanics, you can say, well, before the quantum mechanics was discovered, there were other things. There are fields. So what are the fields? For example, you had electrical and magnetic fields. People knew about them. People knew about light, and they thought of it as a wave. Later, it turned out that it's an electromagnetic wave, so light is actually electromagnetic field. But even more basic than that, when you say what it's a wave, what exactly do you mean? You mean it's a field. So you have some kind of a function, which is defined at different space-time point. So at each spatial point, at each time you have a value of this wave. Wave is just a field, just another name for a field. When it has certain traveling properties, you just call it a wave. But wave is just a name, and it's a name for fields. Or you could say, well, there are no particles. Things are like light. So maybe you can say that we don't have, the world is not made of particles whose motion we can follow like this. Rather, we have these things, fields, something like light. Or so maybe what we have been calling electron is maybe not a particle, it's not a position, it's something like light. It's some extended object, some function f, which is defined on space-time, and whose evolution, now I have to give an equation, give a partial differential equation for the field. And then just follow its motion, and this everything is contained in whatever this function is telling you. So if this field is the field of light, wherever this is more intense, there you have more light. Where its value is 0, you have darkness. Similarly, you can make similar statements about electric and magnetic fields. So it's like you think of that things are like water in a pond. You have certain value of the water level at each point, and if it's going above or below your mean value, that's kind of a field, and you are giving an equation that how these waves move around. And this should have this is how you explain the world. But it turns out this also does not work. So the world is neither particles, at least not in the sense I have described, nor its fields the way I have described. So the two main concepts, they are all out of the window. And why is it so? Why they don't work? So let me just describe to you one experiment. And this is the famous double slit experiment. So this was the experiment which convinced Huygens that the light is actually a wave. So Newton said the light is made of particles. When we see something illuminated, it's just that you have a huge bunch of particles which are striking that thing, and then these particles strike that thing and then enter your eye, and then you get the feeling that you have seen something. Huygens was convinced that it's actually a wave, like a water wave. And why he was convinced? Because of this double slit experiment. So a property of fields, what you can do with fields is that your field has a value, and if you have wave equation as such, for example, I'm not going to write any equations for now. Like if you are considering electromagnetic field, or any wave equation, any simple wave equation, so something like this. A partial differential equation in time and space. This is the simplest wave equation. These wave equations are linear. So what does this mean? It means is that if you have one solution, you have two solutions, you can make their superposition. You can make their linear combination, and that would still be a solution. So even before this was understood about light, that is electromagnetic wave, and this holds for it, people had seen this property of waves, like for example in water, and they were replicating it for light. So if you have one solution, you have another solution, you add, and you get a new solution. So physically what it means is, like, suppose you have a water tank, you are trying to produce some waves here, they're coming from here, some functional value at some point, at some position and at some time, and someone is producing waves from here. So if this wave was not here, this solution would be present, F2. And the water point over here will attain a certain height at a certain time depending on this solution. But when they both are present, something is pulling it up and something is pulling it down, so it would be just a combined effect of both. So this is like in case of the simplest linear differential equations. If you have some non-linearity, then you cannot just simply add, then there will be some interaction, but still there will be some combined effect for both. For simple waves, and this is certainly true, this was found to be true for light, is just that you just add the two effects. So what then you can see, let me just pictorially show you, like so suppose you have the simplest wave, sine wave. And then another wave is coming, which is in phase. So what's happening? You have something pulling it up, then you have another thing pulling it up. So you get even bigger wave as a result. These waves you can think of as being produced because of some kind of springs being pulled. You can imagine, like when you're talking about some fundamental nature, then those springs are some fundamental quantities we don't know, but you can essentially think physically in those terms. So when you add them, you get the whole effect is enhanced. So for example, if I have sine x plus vt plus I add another sine. So I have twice the value for the function. So I'm going to get twice the height. But it could be that one wave is like this, and the other one is like this. So you have introduced a phase shift by pi, any multiple of pi. So then what's going to happen? They both are negative of each other. So they cancel. And as a result, you do not get anything. So the way, this is the fundamental property of wave, that they can cancel or enhance each other. This is just called the superposition of waves. Now, what Huygens did, he was sending light from here, from a faraway source. So you can think of it as like a big water wave coming in, so that you are sure that is the same value, and it's the actual source is way far, far back. So that source becomes like this. So what happens at this point is that you have the same value of the wave or of the function. For example, if I'm describing it by, let's say, sine or cos, I'm writing it as x minus ct, because if it's a traveling wave, that's how it will be. As you change time, you are only changing what is the position of a particular point. So if I have this, at a later point, this guy will be shifted to ct because of this functional form. Now, so what will happen when this light goes from here to that screen? It goes like this. It goes from here to, now let me draw. So you can follow a path. So there's a way going from here. So you think of it like this. And then there's a way at the same point going from here, like this. Now, depending on what's the path difference. So one is coming through some, let's say this is L minus CT. The other one has L plus some other path. And depending on if del is a multiple of, is an odd multiple of pi, let's say 2n plus 1 pi, then it's going to flip the sign. Then the wave is going to cancel over here. Similarly, there will be rays coming in all directions. And it could be that at this point, the path difference is an even multiple of pi. Then they both will have same sign, so they will enhance. So as I move, the path differences change. So I get a bright spot and a dark spot. Again, a bright spot and a dark spot, bright and dark. Because the path differences continuously keep changing. Not only that, this is special for light and for many, many waves, that not only your function is double, the intensity itself, like intensity of light, is actually the square of the wave. So you don't get just like twice the light which you were getting here, you get 4 times and then 0, then 4 times, then 0. So it's even more brighter than you were expecting from just 2 spots. And it has to be like this, because if you're losing canceling some light here, the total energy is not being lost. So that energy should appear somewhere else. So it appears over here. So this phenomena was observed for light actually very, very long time ago, like in the beginning of 1800s. And it was conclusive then that there's no other way. Like, how would you explain it to particles? That particles are landing here and not here, out of these holes. And Huygens knew mathematics well enough that he performed this whole mathematical derivation that how these fringes will look like. And he was convinced, and everyone was convinced after that, that the light is a wave. So let me, just to make it a little bit more clean, draw it again. So it goes from here, goes like that. In the center, you have a big because the light doesn't reach far away. When it's reaching far away, it's being diffused, so you have more light over here. So this kind of, the main point is that you get more light, less light, more light, less light. Well, I should have probably drawn it just to make the point. Of zero light. At some points you have no light landing in there, and at some points it's enhanced. So this was all done, and people knew that this is how the light behaves. Now I'm going to describe to you all the experiments which happened in kind of a fictitious way. What I'm going to describe you, the things really didn't really happen in the real world, but they're equivalent to what I'm going to describe. So instead of light, you say that light is well and good. Let me do the same experiment with the electrons. And when you do it with the electrons, you find that you get the same pattern. Same for light and electron and everything else. Why people didn't see it for electrons? Well, electrons were discovered kind of late, but also this aperture should be proportional to the wavelength. Otherwise, this dispersion doesn't happen. And like you can imagine that if this is big enough, then all the light goes like, it doesn't spread out like that. When it doesn't spread out, you do not get these waves which can cancel each other. It just then is a straight line, a spot here, a spot here. So you need very small apertures comparable to what kind of wavelength of the wave you are using. Now there are all kinds of wavelengths available for light, and it will turn out that there are all kinds of wavelengths available for anything else. But suppose you do it for electrons for appropriate, you don't know, you didn't know that electrons have a wavelength. You just by chance discovered that for some size of holes, you get this. Now you are worried because you have been thinking of electrons and everything else is made up of electrons. Or it's true for neutrons, protons, everything. That you thought that these are particles. I had things in the world which I was describing to Newton's laws as particles, but it turns out that they are waves. Well, you say like, whatever the nature is telling me, I have to accept. So let me accept that everything is a wave. But then you make the observations more carefully. Now what you do, you can do many things. You reduce the intensity and you look over here, look more carefully. When you look more carefully and reduce the intensity, what you find is that wherever you had, and how are you detecting the electrons? It doesn't really matter. Just like we were doing very basic experiments in general relativity, over here you can simplify the experiments as any way you like. So you could have a photographic film over here, electron detecting, any other electron detecting device, like photomultiplier tubes they are used. But doesn't matter. I mean, just take old photographic film where whenever electron it lands, it creates some spot. Anything which could detect the electrons. So when you look carefully with a more careful instrument, which can resolve things to very, very small sizes, and you reduce the intensity, you find that actually I'm not getting a continuous, like I was expecting with the light, that there's some continuous light falling over here, continuous light falling over here, continuous light falling over here. So my photographic film was continuously being emulsed with some intensity of light, and it was continuously changing its shade because of the effect of light. And I thought that this is same happening with the electron, but no, that's not what's happening. What you find is, like, if I start with a blank film, I get dots randomly. And I can reduce the intensity so little that in 1 second or maybe in 1 hour, I get only one dot. So in a sense, in 1 hour, only one electron is coming from here. And what you find that when that electron comes, it's not spread out like a wave, because it doesn't affect the photographic film at all these places where you thought your wave is present. It strikes at a point, just like as if it's a particle. So you say, oh, it's a particle. But when you collect many dots, you find that there are lots of dots here, no dot here, lots of dots here, no dot here, and then again lots of dots here. So this wave then becomes the wave of intensity, where more electrons are landing. So you were interpreting that there's a wave over here, but it was there because the photographic film was more darkened here compared to here. And why it was more darkened, when you look carefully, you found that more electrons were hitting here. So you conclude that after all, electrons are particles, not waves. Why not waves? Because wave is spread out. If it were wave, it would affect the whole film, but it strikes at one point at a time. You get blips. Something strikes, then again something strikes, and again something strikes as one particle. And then you conclude that maybe it's just that the electron's dynamics, the way electrons travel, is very funny. It travels in a funny way so that it chooses to land here and not here, and here and not here. So I just have to find out that law, that kind of weird law, which guides it, which sends it to these spots, but not these spots. So like the first framework I was telling you, you have a position of a particle and you are trying to guess its differential equation, which tells you where the particle moves. Because of this strange behavior, you conclude that maybe it's not the Newton's law which it follows. It follows some very strange, very complicated equation, but my job is to find that differential equation. Now you repeat the same experiment with light. And actually this time you again reduce the intensity of light. And again, look very carefully. You find that there's actually literally no difference between electrons and light. Light also behaves this way. Huygens thought that he had settled that light is a wave, but when we looked more carefully, it turned out that actually the Newton was correct. Same thing happens for light. You get a strike, then after an hour, another strike, after another hour, another strike randomly at different places. But once you collect some thousands of strikes, you find that there are dark spots and bright spots, dark spots and bright spots. So you conclude everything in the world is a particle, but it follows kind of strange paths where, because of these two slits, when there are two slits, they follow some paths so that they land over here, 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 and not here. So now you try to study it in a little bit more detail. And you say that, well, I have reduced the intensity. And now this is what you do now. You reduce the intensity so much that in an hour, only one blip happens here. So in an hour, only one electron is coming in. You want to call it electron, call it photon, because you can do it with anything at your hand. Any particle, they all behave same. So you send the electron 1 at an hour, and you say that it's coming from here, and then it follows some weird path, and it doesn't land always on the same path. So maybe this law is somehow probabilistic. It is some kind of stochastic process. Sometimes it sends it here, sometimes it sends it there, sometimes there and there. But okay, there are some kind of a stochastic equation which is telling it where to go. But what you do now, you know that there is a particle which is coming in, so it will pass through one hole. So what I'm gonna do is, from time to time, I'll close this hole and keep this open, and then close this one and open this one. How could that affect anything? Because the particle is coming in from here. If this is closed, how would it know that this is closed? The particle is here. And what you expect is that sometimes the particle may be coming from this hole and it will be blocked. So I'll get the same pattern, but half of the time it may be blocked, so it may be a little bit dimmed. But otherwise, I'll get the same pattern because the same law will be followed by this particle, this electron. But when you do it, sometimes you close this, then keep it open, then close this and keep this open and wait for electrons to pass through. What you find is that this whole pattern is gone. All the electrons are like, well, you actually get two peaks here. Some electrons land here, some electrons land here, but there are no spots where they have cancelled, where they have decided not to go. There are no interference. This is called the interference pattern. There is no interference pattern. So this is very strange, but what is your conclusion? Your conclusion is that this electron somehow knows that this door is closed. Although it's passing from here, it knows that this door is closed. That's why it doesn't choose to land on those bright spots and avoid those dark spots. It has the knowledge. So how could that be? Well, you say, well, maybe it goes through here. It always is looking for the hole. And if this is closed, then it comes back and then chooses this spot. If this is open, then it goes through and comes back and chooses the interference pattern. Now, this is already looking like a very, very strange kind of law. And how will it check that where the holes are? It will have to keep checking everywhere. But we are desperate and we assume, well, the differential equation is extremely complicated. And this guy, and also it has to know that if it's closed here, I have to come back and keep checking unless I find a hole. And for how long it will keep checking? If it doesn't find a hole, it has to come back and do it. But you say, fine, maybe something very, very strange is going on. Maybe this is what it does. So what you can do is you can try to see over here that which hole it passes through, and does it goes through both holes, tries to go there. Another kind of explanation you can give is that the electron, when it comes here, there are these two holes, it keeps splitting. It's kind of same what I first described. It splits, goes through both, and when this one is, both are open, then half electrons goes from here, half from here, and then it produces this interference pattern. But if the half electron is here and half is here, this is like saying that it's not a particle, it's like a wave. It's spread out at two places. This is the main property of wave as opposed to particles. Particles are positions at a point. Waves are fields in space. So this is exactly what the wave does. Wave is blocked everywhere else. It starts at this and it starts at this, and that produces this pattern. You don't want that, but because you know that it doesn't split here when it strikes here, but you say maybe it splits here and then recombines. So then you try to check this hypothesis. Because why I'm saying it splits, or why I say that it keeps checking, because the pattern appears when the other hole is open. So how would the electron know that the other hole is open? It has to do something. So you check over here by putting some detectors, very gentle detectors, maybe some kind of a bubble chamber, so that when the electron passes, you are informed that the electron has gone through this hole. And you are expecting that since this interference pattern is produced only when both holes are open, so somehow when one electron comes, it's present at both. It checks it out. What you find is extremely strange. What do you think? What do you find? Any guesses? Is anyone alive?
Yes, sir.
So what, any guesses?
Yeah.
What could happen? So you are checking here. What do you find? Which hole it passes through? Both? If
Sir, the one that is nearest to it.
No, there's no point of nearest, because these are coming from here, from far away. It's just like the light. And so there's no concept of nearest. You don't know which way is coming from over here. But if you say that it goes
it may
from
be
one,
possible that electron travels in a straight line, so whatever that is feasible to it, मतलब जिसके through ये जा सके.
अच्छा, अगर तो ये किसी एक में से जाता है, if it goes from one, then first question is how does it know that the other hole is open? क्योंकि अगर other hole, if I close the other hole, I don't get the pattern. If I
Sir, ये भी तो होता है कि मतलब जब
if I let me just finish. If I keep one hole closed, then the pattern doesn't appear. तो अगर वो यहाँ से गुजरा भी है, तो how did it know कि ये hole बंद है?
Sir, because जब travel करता है electron तो ionization करता हुआ नहीं जाता है, मतलब particles की जो air में present.
नहीं है, it's vacuum.
Okay.
But I don't know what ionization has to do with it. It has to know कि ये hole open है, and it's vacuum. तो अगर वो एक hole से जाता है, how does it know कि दूसरा hole open है? क्योंकि there's a physical difference which appears. If I close it, the जो electron pass ले रहा है वो change हो जाते हैं. It doesn't land on the same spots. It lands on the other spots. एक तो ये problem है. लेकिन जो असल में होता है वो तो मैंने डिसाइड करना एक्सपेरिमेंट क्या बता रहा है, तो वो ये भी नहीं है. passes to one
तो
hole.
सर जो फिल्म है जो बेसिकली कलेक्टर है, उसको अगर हम उसके पॉजिटिवली चार्ज कर दें तो वो फिर एक ही होल से जाएंगे, मतलब
नहीं, पॉजिटिवली चार्ज मैं नहीं कह रहा. आई एम नॉट ट्राइंग टू डिफ्लेक्ट द इलेक्ट्रॉन. आई एम ट्राइंग टू just see it as gently as I can. और अगर मैं positively charge कर दूं कि वो इसी होल से जाएं, और and then I know कि वो सारे इसी होल से जा रहे हैं, then you know what will happen? This pattern will not appear.
Say.
That's exactly what happens. So you force them to go from one hole. It's like you have closed the other hole, and once you have closed the other hole, the pattern doesn't appear. So any other guesses what happens?
सर क्या कोई अंडरलाइंग फील्ड है जो
नहीं, फील्ड है या जो भी है, इसके बारे में क्या कह सकते हैं? अगर आप कह रहे हैं फील्ड है, तो फील्ड होगी तो क्या होगा कि मैंने यहाँ डिटेक्टर रखे हुए, तो आई विल डिटेक्ट द फील्ड एट बोथ प्लेसेस, राइट? दिस इज द होल आइडिया ऑफ फील्ड, कि अगर वो यहाँ भी मौजूद है, यहाँ भी मौजूद है, देन आई विल फील इट एट बोथ प्लेसेस, राइट? तो यही मैं चेक करना चाह रहा हूँ, क्योंकि बिकॉज somehow it knows about both holes, so I want to check is this field present at both places? So your guess is, first guess was कि एक से जाता है, लेकिन अगर एक से जाता है तो दूसरे का उसे कैसे पता? और दूसरे ये कि जब मैं actually experiment करता हूँ, what I find, it doesn't go through both. It goes through only one. I detect it either here or here. But the most strange thing is that once I have put in these detector and I have this knowledge, I try to do it as gently as possible. I just try to have this information with the best possible way. As soon as I have this knowledge that the electron was here, it's like as if electron is part of a conspiracy. It knows that I have this knowledge. And again, this interference pattern goes away. Since it passed through one hole, so it wasn't like field, it was like particle over here. And this particle, then this wave was not there, only this wave was there. So it's present, the interference pattern goes away. So if it's a particle, it goes through only one. Then the question is, when I open both, why does it show the interference pattern? So it's kind of a field which is present at both places, but also it's something which when I try to detect, it's a particle. It acts like a particle. It appears at only one place. So it's neither field nor particle, but it's field as well as particle. It has both properties. And how to think about it? This is what we will learn during the course. Okay, what does it mean that it's a field, but also it's a particle? It has to be a field because it was present at both places. And if I was assuming that it's particle and it's just that its path is such that it knows about the other hole, then when I checked, it doesn't do that. It only passes through one, but when it does it, the interference pattern is gone. So it's like a conspiracy. When I'm not looking, it acts like a field. But when I try to look, like when I try to look over here, it strikes as if it's a particle. And what else I can do to check it? So then you can say so I think this is just an introduction to give you an idea that what kind of strangeness is present here. So any question, any other proposal which could explain it as a wave or as a particle alone, or as a wave and particle.
सर इसमें अभी हमने एक होल पे डिटेक्टर रखा था ना, तो अगर हम
दोनों पे रखा था.
अच्छा दोनों पे रखा, सॉरी.
So any proposal, any idea where I could explain this experiment as if it's a particle, taking any complicated path.
सर अगर लेंस रख दें कोई तो वेव होगा तो
मैंने अब ये कहा ना कि this is like completely idealized. It doesn't matter what method you are using. Lens रखें, bubble chamber रखें, photographic plate रखें, कुछ भी रखें. Gentlest possible, anything you do, the moment you try to see that which hole it passed through, the interference pattern will go. As soon as you know that it's over here, the interference pattern will go. So you wanted to see it as a wave, so that it's present at both, because you know that there's a wave coming from both holes which is causing it. But you don't see it. You only see particle. But once you ask then how this interference pattern is produced. It's produced when you were not looking, when you were not deciding which hole it was passing through. Then as if it was passing through both. But you can check it. The moment you check it, there's no logical inconsistency. It's just that it's extremely strange. And it proves that either of those formalism of thinking of this thing as a particle or thinking of this thing as a wave, experimentally, both are ruled out. Obviously, it has some features, like I do detect it as a particle when I try to see it. And I can explain its path to some wave. So both features are there, but it's not either one of them solely. So any question about it?
सर ये क्वांटम के उसके ऊपर डिपेंड नहीं करता कि सॉरी इलेक्ट्रॉन के इलेक्ट्रॉन कॉन्शियसनेस के ऊपर कि इलेक्ट्रॉन को पता चलता है कि कोई चीज डिटेक्ट कर रही है देन इट चेंजेस बिहेवियर.
Well, if you want to make such a theory कि electron के अंदर भी consciousness है and it is part of such high conspiracy that it knows that someone is detecting, and first of all detect कितना gently कर रहे हैं. It has to be then like an extremely like the, well, it's like an all-knowing electron. Because no matter how gently you do, the moment you have knowledge, it has knowledge about you. And also, then you will have to make a theory. You in the end, you want to write some equations. And then you will have to somehow model the consciousness of electron. So in a sense, we are modeling the consciousness of electron in this theory. You want to call it consciousness or whatever, like some computer register or whatever you want to say. This is what the experiment tells us. The moment we know, the electron changes its mind.
Okay.
But I would rather avoid this word consciousness, because in the end, I'm going to give you a mathematical theory which explains it. You want to call it consciousness or whatever, that's fine.
Thank you, sir.
Any other question or any other proposal which could save it in the favor of particle or the waves? Okay, so one thing you could say is that there is some wave and a particle, and the wave is made over here. These waves are interfering and making a pattern, and this electron then tries to follow these waves. It goes to one hole, but it tries to follow these waves. And when I close this hole, one of the hole, this wave is gone, so that only one wave is present, so it follows only that wave. But then this also raises a question, and the question is that when I detect the electron over here, then what happens to this wave? Then why doesn't it follow this other wave? I didn't close the other window. What happened to the other wave? If this wave was present and I detected this electron, why did not it follow the other wave, which should have created this pattern? So even this explanation that it's a wave, it's a particle following a wave, even that doesn't work. So I can then go on and I can actually give you an explanation which would work, but I think I should avoid discussing it today. I don't want to give the answer right away. Rather, I would first try to develop the theory. And now the theory can be developed in two ways. One is like, I'm talking about these kind of wave motion, which I suspect to be wave motion. I develop some mathematical machinery about those waves, and then take the help of experiments to see that what can I conclude? How can I explain, for example, this experiment? But that would be like dealing with differential equations and doing some Fourier analysis. I would rather go to more abstract theory directly, because that's what we need in the end. So again, this is not the path I'm going to take, which I described as the first kind of course where you follow the experiments. I'm not going to take that. I'm going to start with telling you the theory first, and from the consequences of theory, I'll show you that those postulates can explain it, this. and actually everything else in the world which we have seen. So now we're gonna move to the postulates of quantum mechanics, describing what the theory of quantum mechanics really is. Right away, going into postulates. So the first one is that a quantum system and what do I mean by a quantum system? It could be anything, a particle, electron, an atom, molecule, light, human, spaceship, anything of interest. Although we do know that there's a range of validity of classical mechanics, not of quantum mechanics. Quantum mechanics in principle should be valid for everything. Classical mechanics is good enough for large objects. We will also learn how to actually see what is the boundary, at what, how can we decide that this object can be effectively described by classical mechanics. But classical mechanics is good enough, like it's a approximate theory for bigger objects. Like we will be wasting our time if I am trying to describe quantum mechanics, spaceship to a quantum mechanics, because classical mechanics will give exactly the identical results. So mostly it's relevant for small systems, but not always. Actually, these systems can sometimes be very, very big. By big, I mean even like micron size. But in principle, any quantum mechanical system, and when I'm thinking theoretically, like for example, I'm describing a quantum field, then this field is diffused all over the space. So I don't know in what sense I should say small. But in any case, any object, any system of study, anything in nature which you isolate to study could be a quantum system. And the first postulate says a quantum system is not described by position or any wave or anything like that. It's described by a vector in a complete linear space called the Hilbert space of the system. I'll come to this terminology, Hilbert space. In mathematics, it has a very specific meaning. We won't be concerned with that meaning. That is there. You have to make it a Hilbert space because of technical reasons. We will only deal with those technical reasons when we encounter them. I won't be discussing much about the Hilbert space structure of these spaces because it's just technicality. It will take us towards deep analysis kind of discussions, which I don't want to do at this point. Probably I'll give a lecture later on this, but I'll just make a comment that what does it mean. So for now, think of it that it's a vector in a complete linear space. Well, when I say complete, that is, this terminology already means that it's a Hilbert space. All finite dimensional spaces, well, I should put another word here, complete complex linear inner product space. Or I could have said by a vector which is a complete, which lives in a complete complex normed linear space. This whole thing is actually the definition of Hilbert space. So what does complex means? Complex linear space just means that it's a vector space. Normed mean that there is a scalar product on it. Complex means that the field with which you multiply these vectors are not real numbers, they are complex numbers. This completion, this only enters when you are considering the infinite dimensional spaces. Because for finite dimensional, you always have, you can show as a theorem that you have the basis. So this property of completion is there when you have infinite dimensional spaces. So it's hard to talk about the basis, and in that case you have to define the basis more carefully, that because you are having a sequence, a sum of an infinite sequence, so you have to make sure that they converge properly. So that's this part is only there for those infinite dimensional spaces. So it lives in this kind of a space, and you denote it. Actually, the notation is also very important. The element of this space are denoted by this kind of an object. So psi is its name, and it's written in this kind of a parenthesis, which are called the cats. So they belong to the space, which are usually denoted by H for Hilbert. And so let me just describe all these terms a little bit more in detail. So that's the first postulate. It's complete over here, that it lives in a Hilbert space. If you knew about what Hilbert space is, we are done with the first postulate. But I suppose people are not, all of you may not be familiar with it. So let me just say something about it. Now, so what is a complex linear space? Complex linear space with inner product. So you have these objects in it, and you can make linear combinations. If you make a linear combination with alpha, beta belonging to the complex number, then it's also in the same space. That makes it the linear, and the usual distributive and all those things, they are there. So I'm not going to go into extreme detail because I assume that everyone knows at least the linear algebra with real numbers. So it's a complex vector space. Then it has a scalar product. For complex spaces, the scalar product is defined this way. So what is the scalar product? For each, you take any pair of vectors from H, there exists a map this scalar product map takes it to the complex numbers. This is some number, complex number, which I'll just denote by this bracket. My pen is broken today, so writing is not very clear. So you have this numbers formed by these pairs of vectors, and this is the scalar product. And what are the properties it satisfies? So usually you take it to be symmetric, but in case of complex, you do not have complete symmetry. You put this condition. So phi psi give you a number. If you change the order of psi and phi in this machine, in this scalar product, then you get the complex conjugate of the original number. And this one is still there. That if you compute the scalar product of a vector with itself, then this is bigger or greater than, then this is a positive number. And it's equal to 0 if and only if this vector is the 0 vector. And also, as usual, this scalar product is linear. If you have this, it breaks. Like this. The only thing, so these are all the obvious things, but the only thing to notice here is this. That it's linear in the right hand, right vector, but if I put something here, then by the property of the scalar product, I can invert them. And I get a star. Now I use the linearity. And this becomes this. I should have discussed this. This is part of the postulates. So this comes out as a star. So that means this thing is like this. You get a star if you use linearity on the first argument. Now you can have the usual things. So this is just a definition of basis. A complete set which is also linearly independent is called a basis. And by complete, I mean I can write any vector as a linear combination of these vectors. So this set is complete if any psi can be written like this. Now, if they are also linearly independent, then it's a basis. The converse is, so any complete set which is also linearly independent is just a basis. Now, what I can do is I can run the Graham-Schmidt process to convert first of all, if they are not linearly independent, then I can strike some off that's like obvious, and get a linearly independent complete set. I can get a basis. If I have a complete set, I can get from that a linearly independent set, which will give me a basis. And I can run the Gram-Schmidt process to convert a basis into an orthonormal basis. Actually, even if I have for a subspace, V of my Hilbert space, if I have a basis here, I can run Gram-Schmidt inside the subspace to get orthonormal basis for the subspace. So in each subspace, I can always have an orthonormal set if the bases exist. And you can show, this is easy theorem, not going to prove because I am assuming that people know. I'll do a little bit whenever some complex use of complex properties is going to enter. I'm probably going to show you the proof, but these are like very basic from vector spaces, that orthogonal vectors are always linearly independent. But the converse is not true. If you have linearly independent vector, they may not be orthogonal, but then you can run the Gram-Schmidt to get orthogonal vectors. Now, so that means that if I have a basis, I write these like this, where I is a basis, and if I is an orthonormal basis, then I can get these numbers. These are called the components of psi in basis I to the scalar product. So psi I would be given by, if it's an orthonormal basis, by psi scalar product with I. I'm just going to show it because I'm going to use some new notation where these terms, which you know already the proofs, where it will be worthwhile to just do it in that notation. So what's the notation? Well, let me say one thing before I go to that notation. And so there's this theorem that number of vectors in any basis is same, and that's called the dimension of the vector space N, but nowhere I'm going to assume that this dimension always has to be finite. Can be infinite. It's very important. Actually, let me make a remark here. In actual world, all quantum systems live in an infinite dimensional Hilbert space. that's just the fact. It's reminiscent of the fact that a particle can have any position. It's a continuous variable, infinite values of position. So that kind of translates into that the quantum systems live in an infinite dimensional Hilbert space, even the simplest one. But we can focus on some properties of quantum systems which may be living in finite dimensional Hilbert space. And fundamentally speaking, the way this theory is set up, they can be systems which live in finite dimensional Hilbert spaces. You can cook them up in your mind. There's nothing stopping you. There's nothing which goes wrong in the theory. It actually only simplifies the theory. But the real systems are actually not like that. But we can focus on some properties of the system so that describing those properties only needs just finite dimensional Hilbert space. So let me write focusing on some limited properties may lead us to deal with only a finite dimensional Hilbert space. So for example, if you're studying spin, then you do not need the infinite dimensional Hilbert space. Those finite dimensions just do fine. That's all you need for that. So, but in our general postulate, the space could be the vector space where these vectors live can be finite dimensional or infinite dimensional. So when they are infinite dimensional, that's where this Hilbert space thing comes in. Wait. So what is this Hilbert space? Since we can, if it's a infinite dimensional vector, then all you are saying is that you will have things like these. And then convergence becomes important because it depends how you are summing this series. So the what goes on into the Hilbert space is that if I make this object, that they exist, so what is a complete Hilbert space? What's an infinite dimensional Hilbert space? And this is just only a technical comment, which I will keep coming back from time to time to make it more precise or more elaborate. For an infinite dimensional space, if maybe I should write it this way: if a vector space has a set has only sets, complete sets with infinite number of vectors, then it is called an infinite dimensional Hilbert space. And in this case, the way you define complete sets is the following. You take for any psi, so you have this complete set. Complete set And you should think of it, right now I'm speaking technically, but you should just think of it as the basis vectors. It's just that they are infinite in numbers. But for technical reason, you define it this way: for the complete set I, and any vector in any vector psi in your Hilbert space, if you make this object, there should exist some linear combinations like this, vectors. Let's call it, let's give it a name. What should I call it? Let's say psi tilde. So in a sense, this difference is going to 0. But how do you define it? You say that this scalar product of this vector, in what sense is 0? Because you cannot cancel it against it unless you know how the basis match. It's about matching of the basis. If you expand it in one and you don't even know how to expand it, so you just say that some kind of expansion exists, so that this, when this n goes to infinity, this is, the scalar product is 0. So that this is approaching to a 0 vector. And so you are successively putting members in this set. And when you include all of them, when n is going to infinity, it's you're including more and more. This guy is becoming closer and closer to this. And it becomes equal to it in this sense, that when the n goes to infinity, the scalar product is 0, so it's approaching the 0 vector, or this guy is becoming close to this. So you can say that this expansion is dense in the Hilbert space edge. You can come as close to any psi as you like by making an expansion. It's just like an analytical technical comment, but this is how you can define it exactly. But to think of it is just that you have these basis vectors pointing in different directions, and you have an infinite number of them. Any question? Now, let me come back to, so we are right now still at postulate 1. I'm just explaining it, that's explaining the mathematical objects which enter into that postulate. That's all we are doing. And the postulate itself is just saying, if you notice that, what did I say? That I said that with each system is associated a vector. What does it mean that associated? It's just that the system is described by that vector, but what to do with that vector? What it has to do with what we measure in labs. Like we measure positions, the trajectories, or whatever you were doing in this double slit experiment. What it has to do with that vector, that will come later. Right now, it just says that all the information you have, this is actually very important, maybe I should write, all the information about the system you can ever have is contained in this vector psi. Now, some notational remark, which is very important. So, with each psi, let's say, yeah, for each psi, I can consider a linear functional on my Hilbert space. How? I construct this scalar product. In the first place, I put in this psi. And over here, I can keep putting my vectors and I keep getting numbers. Like this. So each psi gives me a dual vector. To scalar product. And so this psi is mapped to the dual space. Let me for now write like this, but later probably I will not even use this symbol, it will be understood. And the members of the dual space I write with the opposite kind of bracket, and these are called the bras. Dual space. So then I can just say that the action, so if I have a phi, I have a dual, it's called, some people call it conjugation, or through dual operation, I get the bra. This was a cat, I converted it into bra. So for each cat, I get this operator bra, which can now act on my vectors to give me the number. And what number? Is just this number. So now you see that with this kind of notation or this kind of language, the scalar product can be thought of as action of bras on the cats and can be written as this symbol. So I'll be mostly writing like this, the scalar products. So in other words, if you have psi 1 and psi 2, and you want to write the scalar product, you just write this. The order matters in the scalar product. You just write like this. And it's understood that it means this thing. But over time, you forget writing this and you just start doing this thing. Now, another thing to notice because of this notation is the following. So I can multiply my vectors by numbers. So if I have a vector phi, I multiply it with a complex number a, it gives me a new vector. I can give it this name, a phi. Then this bra, so this was cat, I make it a bra and act on a vector to make the scalar product of this guy with psi. This is actually equal to this guy, which is actually equal to this guy, which is a star, which is actually phi psi. So you see, if I have something like this, again, the A comes out as it is. But if I have something like this, because of the notation, it comes out like that. So the dual, you can say that the dual of a phi is a star phi. Now, again, as the notation goes, any vector psi in an orthonormal basis can be expanded as like this. If it's an infinite dimensional space, it will go from 1 to infinity. Otherwise, it's some finite number, but I'll mostly just leave it ambiguous. Then we often imagine this thing as giving us a column vector. This is not a column vector, this side. This is some abstract object, but I can collect the components and arrange them in a column. Like this. And if it's an infinite dimensional Hilbert space, it's very useful to still think of it as a column, but an infinitely long column. It keeps going. Then what you have is that I can write with each psi given a basis, I can associate its representative column in that basis, which would be this. And as usual, I can write it like this. So in that basis, the representative of the basis vectors would be just the standard columns. Now using this notation, just observe the following. If I expand so notice this notation. If I denote this psi, if this is vector by a psi, usually, but not always, usually I write the components as psi I. So psi i's are complex numbers, which are the components of psi. And i's are the basis vectors. And if it's an orthonormal basis, I can do this psi I is being multiplied to I. So it comes out by linearity. Now, this j and I are orthogonal unless they are the same basis vectors. Whatever indexing you have done, you have made sure that they are all orthogonal. And when the vector is same, then you get a 1. So you will get psi j. So the jth component can be computed by taking this scalar product. And you can see another thing, another nice thing. If I want to do this, compute this, then what do I have? I have, well, let me write it this way for practice for now. This is summation I, phi I, I, and then summation j. I'm just changing the index. This comes out as phi I star because it's in the first position of the scalar product. And we saw that when you pull anything out of here, you get a star. And this comes out without a star. Now again, these are orthonormal. So you get a 0 unless I is equal to j, and then you get a 1. So you get summation I, phi I star, psi I. Now you can see it that I can think of it as if I have taken this column and multiply it with this row. By matrix multiplication, this will give me this number. So you can think of this bra as a complex conjugated row of phi. If phi is a column, then phi cat is a column, then phi bra is the complex conjugated row. That's why it's called the conjugate. Some people just call it conjugate of psi. So let me actually give you an example of an infinite dimensional space. So when we will be dealing with infinite dimensional space, as I said, that we will not be mostly concerned with the analytical properties. Sometimes they become very important. Sometimes you do not are not paying attention, and then you get a completely junk, completely nonsensical result, and then you have to go back and see that what analytical mistake you did. But for us, most of the time that will not happen. We will just wait for something to go wrong to be more precise about it. We will be mostly hand wavy about dealing with infinite dimensional Hilbert space. You may not, if I hadn't made this comment, you might not have even noticed that I'm being hand wavy or I'm not being precise. It's just that I'm not will be using the full machinery of analytical Hilbert spaces because it's not needed. Let me just tell you how we're going to deal with the infinite dimensional spaces most of the time. A little bit of cheating will be involved. Well, not cheating, it will be just a kind of a point of view which is not very precise. But let me first give you some example, example is correct, but the way we will deal with it is not how most mathematicians would like to do actually. Okay, let me give you an example. So for example, you can consider an interval AB, let's say of length L, and you can consider the L2 functions on AB. So that means they belong to the continuous function on AB. And so FG, all functions which are defined over this such that this integral exists. So these are the ones which live in this L2 space, and these are this forms a vector space, a complex normed linear vector space. Well, first of all, it's obvious that it's if I add two of the functions, it's still in the same space. That's all good and fine, and I can check that this is, I can define the scalar product by this very thing. This is a complex scalar product. Well, most of the properties are obvious. The only thing I can check is if I give it the same guy, this will be bigger or greater than 0 because I have a norm square over here, and it will be 0 only if f is 0 identically. It's just because of the Riemann properties of the Riemann integral. And linearity also holds. To this integral breaks up, and it is really this thing. Now, you have to give a set. For it to be a Hilbert space, you have to give a set so that you can expand any function over here in a Cauchy sequence of that set so that it's dense in that. Now, that is the statement of the theorem of Fourier or whatever, whoever did this, that you know that a Fourier expansion for these functions exists. So I can write any function like this so that it's arbitrarily close to my desired function. And these guys, you really have to include all these functions, and goes from -infinity to +infinity. So this is a complete set. In this, and this complete set is obviously infinite dimensional. If I consider all the functions, I have to have this infinite dimensional complete set if I want to expand them in some kind of expansion. Another option is that you consider these guys. And then you make them orthonormal. Because actually the property which I had written for it to be a complete set, the part of it was that you have to take an orthonormal complete set. Only then it made sense. So when you make it orthonormal by Graham-Schmidt, it gives you the Legendre polynomials. So you can use some polynomials to expand them, or you can use the Fourier components to expand it, and but you need an infinite number of them because it's a functional space of functions is infinite dimensional, and it's truly a Hilbert space because of Fourier's theorem. But most of the time we won't be dealing with, well, we will sometimes deal with the Fourier series, but it's very there's a question. Graham-Schmidt is the standard thing. You can just go and look it up in any linear algebra course. We won't be running it through. Most of the time, our things will come out to be already orthogonal. Now, most of the time, we won't be, it would be very helpful if we think in terms of something else. So we consider, for example, if I consider this kind of functions on this interval AB, and I take a function, take its graph, and so I think of it that I'm describing it by giving its value at each point. So these are the points. Now, obviously, I can't really describe it in this way because I will have to give its value at each point, which is not countable. And the way I was describing it over here, like over here, the basis elements were infinite, but they were countable. So there's some kind of an approximation you use, an approximate description. Of choosing continuous label and making it approximate to countable to represent the basis. Okay, so how does it go? Well, I can think of it just like you do it in case of the Riemann sum. You just consider that you have divided it into a large part and there's only a difference of delta, where delta is very, very small over there. And then you say that I'm gonna, because what is the basis in any case? Basis is some kind of a, is going to be some kind of a vector. And so you want to describe the components of your vector, which is f, which is just the function f. F is the function. And corresponding to it, you are thinking of this function as an abstract vector. And how can you give this abstract vector? You have to give its components in some basis. So instead of giving its Fourier components, you say that what I'm going to do is I'm going to tell its value at each point. And think of these things living at each point as some kind of a basis. And it's like a continuous basis like this. And then this then gives me the definition of this basis. So I'm describing this vector because I can really do it if I choose a huge number of points. Then these components do describe for me this vector, this function. So I just say that the expansion is just collection of these components, the value of function at each such point. And I think of them as the components of my vector of my function in this basis, which I am calling, this is some basis, which I am calling the position basis. And not only this, you just multiply, you just don't give these components, you multiply them with this small element delta. Because in some sense, you want this thing to come in there, and these components are in some sense large, but since you are moving in a continuous fashion, you should make them small by multiplying with this. So this is just a definition. But with this definition, you can do this. You can take delta to 0, n to infinity. Then this thing becomes dx. This is how you represent it. And the idea is like you're sampling this function at each point in space like this. Now, you want, now with this definition, let's see what happens to the scalar product of two functions which live in this space. So this G is also expanded in same way. And when I do this, I have J1 to N, I1 to N, G star, because it's going into the bra. Remember, when you have a number multiplying the bra, then it gets a star in front of it, on top of it. So I have then Xi, Xj, f of Xj, and then I have a delta, and I have another delta. And now I want that this is a small number. When I multiply them, I know that this guy, I had defined its scalar product this way. This was the definition. So when I take the limit, I should get something like this. So how can I get that? There's something in between over here, which is going to be a number, but I just need one delta to convert this sum into an integral. First of all, these are supposed to be orthonormal. This is all part of definition. I am taking them by hand to be orthonormal. If they are orthonormal, then xi, xj would be 0 if I is not equal to j, and xi, xj, if I put it equal to 1, what will I get? I'll get two deltas. This sum will break because I get a 0 whenever I is not equal to j. F of xi, two deltas, and I get a 1. But because of these two deltas, I can't take the limit and get a finite number. So I should put this equal to some, again, vanishing delta. So xi, xj is like proportional to this. And when I take this limit, one delta cancels with this, and this gives me the integral which I want. This was a to b. This delta becomes dx. Now, I'm not going to be using this discretize. Every time I'm not going to discretize it. So I'm just going to invent a notation in my mind that I have this idea that I'm discretizing and approximating, but or approximating, by approximating I mean I'm taking limits. But I will use a continuous label for these position basis vectors. So just write like this, and this x can take any value. X is a continuous variable, and it takes values between a and b. And I define the orthonormality through this function, the Dirac delta function. So everyone has seen Dirac's delta?
Yes.
Yeah, so then it's quite obvious that once I do this, then what happens? Then if I expand f like this, now I just use the continuous labels like this, and then this is just a b. When I take the conjugate, these are like components. F of x should be thought of as a component of f in the direction of x. So f of x is component of f in the direction of x. So it gets, so this g gets multiplied, it gets conjugated. F of y, you have a dx and dy, x, y, dx, dy I have already written, and xy gives me a delta function. And then by property of Dirac delta, I get which was the definition of the scalar product. So the idea is that just this notation, or you can say that this construction of writing this f like this, and the manipulations which we have defined, properties which we have defined for this just gives me a kind representation, a nice representation of expanding this vector in a particular basis which I have just constructed. Actually, it turns out that this basis, we will probably see it next time, this basis does not actually lives in the original space. So it's not, technically speaking, it is not part of the Hilbert space, this X, but it's very useful. So we just work with it. So you can just say that in the quantum mechanics I'm doing, where I'm not being super careful that I'm not making any analytical mistake, I will not be dealing with the basis from the Hilbert space. I'm working in a Hilbert space, but for my convenience, because this basis has very nice properties, I work with a basis. I expand my definition of a Hilbert space. I start with a Hilbert space, and in that I throw in this new basis. Why it's not in the Hilbert space? Because this is not square integrable. Xx dash is delta, and x, if I take this is a distribution at same point, so it blows up. So this it has this kind of a problem, but it's just a technical problem. It helps us a lot. So you can say that I have expanded the definition of Hilbert space slight bit to include these because they are very helpful. Now, what now? Okay, now let me take an attendance. So I want a question from everyone. Asma has already asked me questions, I guess. Frida, you have to ask a question. I'm not done, by the way, do not leave. I have to say a few more things. Frida, you're not there? Habiba, you have to ask a question.
Yes, sir. Sir, I have no question.
Huh?
No question.
You have to ask, that's the deal. आप कहीं बाहर हैं?
जी सर, वापस जा रही हूँ घर यूनिवर्सिटी से।
चलें ठीक है। And now who is next? Mayam, what's your question? Ask anything. आपने वो, have you heard that saying that there are no stupid questions, there are only stupid answers? So, Mayam just left. Fizan,
यस सर।
question तो पूछे।
सर ये ड्राग डेल्टा फंक्शन का पूछना था सर।
क्या?
सर ये इन्फिनिटी पे जनाब जो 0 हो रहा है और जनाब जो 0 पे 1 आ रहा है।
नहीं, ड्राग डेल्टा फंक्शन अगर आपने नहीं किया हुआ, आई वुड सजेस्ट कि इसको थोड़ा आप जाके रिव्यू करें। It's
जी
not
सर।
really a function, it's called a distribution, but if you want to have a picture of it, अगर मैं x minus x dash लिखूं, then it's a function on x with a special mark on x dash. So it's 0 everywhere, and then it's like a very high peak at x dash. So it's like infinite at x dash and 0 everywhere, but that infinity is such that if I integrate it, I get a 1.
ओके सर।
So if I write this, if I integrate it with any function, it evaluates that function at that point.
सर ये नेक्स्ट क्वेश्चन ये था कि हिल्बर्ट स्पेस में जनाब जी ये ऑर्थोनॉर्मल वगैरह का किस तरीके से पता चलेगा?
ऑर्थोनॉर्मल कैसे पता चलेगा? वेल, एक तो ये कि आप चेक कर सकते हैं, ठीक है। Many times when you are setting it up, you just declare कि ये मेरे पास ऑर्थोनॉर्मल बेसिस है, because they are just symbols. हम जब कहेंगे ना, for example, जब हम spin कर रहे होंगे, they will be just symbols. We will just say कि these are the orthonormal things, because that's how we will set it up. लेकिन जब आप एक concrete किसी चीज सिस्टम के साथ डील कर रहे हैं, तो you will get something and you can check if it's orthonormal or not. ये जो for example ये जो basis है x, इसको हमने by hand, इसको part of definition है, हमने कहा है कि हमने ये एक basis vectors लिए हैं which are orthonormal in this sense. समी,
सर ये
हाँ आपका और क्वेश्चन है?
सर ये कैसे मुमकिन हो सकता है एक चीज वहां पे मौजूद भी और नहीं भी है? प्रोबेबिलिटी किस तरह ले रहे हैं हम यहाँ पर?
कौन सी चीज?
ये जो हिल्बर्ट स्पेस में होता है ना कि हम जनाब जो कभी वो ये अनसर्टिनिटी प्रिंसिपल जो लगा रहे होते हैं,
अनसर्टेनिटी प्रिंसिपल तो कहीं आया ही नहीं।
नहीं सर, ये जो हमें हिल्बर्ट स्पेस में कहते हैं ना कि जब वह जगह तो जनाब जो 100 प्रोबेबिलिटी है कि यहाँ पे इलेक्ट्रॉन पाया जा रहा है।
या मैंने कोई प्रोबेबिलिटी की बात की है?
नो सर।
तो नहीं, तो let's just go in sequence the way I'm developing.
Okay.
अच्छा समी, फिदा ने भी कुछ पूछा है। समी आपका क्या क्वेश्चन है?
सर ये जो ब्रैकेट की जो नोटेशन है इसको हम इनर प्रोडक्ट के तौर पे ही देख रहे हैं ना, क्योंकि हिल्बर्ट स्पेस में इनर प्रोडक्ट स्पेस में ही आती है। ये
हाँ, ये ब्रैकेट नोटेशन is just a way to represent the inner product. Exactly. So if you go back and try to look it carefully, that's exactly what I said. Okay, when you are making the scalar product of psi and phi, आप इसको ऐसे भी देख सकते हैं कि phi is a dual vector acting on psi. Every scalar product for you, you have a scalar product that defines for you, it gives you a map to the dual space. तो इस स्केलर प्रोडक्ट को ही मैं अब इस नोटेशन से यूज कर रहा हूँ, bra phi and acting on psi cat. कुतुलैन आपका क्वेश्चन? और क्वेश्चन था आपका?
ये डुअल स्पेस जो फंक्शन में ही पढ़ते हैं सर, इसी चीज को ही हम कंसिडर कर रहे हैं ना, डुअल स्पेस। जो
डुअल स्पेस आपने वेक्टर स्पेसेस में पढ़ी है?
जी वेक्टर स्पेसेस में
नहीं पढ़ी?
जी सर जी पढ़ी है। जी सर।
हाँ तो ये वही है, ये आपके पास वेक्टर
जी।
स्पेस है H, हिल्बर्ट स्पेस फंडामेंटली वेक्टर स्पेस है, उसकी ये डुअल स्पेस, एंड यू कैन गो चेक के सारे जो है ना पोस्टुलेट डुअल स्पेस के वो पूरे हो रहे हैं इस पे। लेकिन the best way to think of it is just a notation of taking the scalar product.
सही 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 सही। ठीक है सर, ठीक है।
और कोई तो लाइन आपके क्वेश्चन?
सर ये जो क्वांटम सिस्टम हम डिस्क्राइब कर रहे हैं, ये सिर्फ हिल्बर्ट स्पेसेस के लिए हमने बात की, तो इसके अलावा भी कोई स्पेस ऐसी है जिसके लिए हम क्वांटम सिस्टम को
नहीं,
डिस्क्राइब
हम
कर
हिल्बर्ट
सकते हैं?
स्पेसेस के लिए क्वांटम सिस्टम नहीं डिस्क्राइब कर रहे, हम क्वांटम
मतलब जो वेक्टर हमने लिया है,
क्वांटम सिस्टम्स के लिए हिल्बर्ट स्पेस हमें चाहिए। दैट्स द फर्स्ट पोस्टुलेट। इट सेज कि अगर आपने किसी क्वांटम सिस्टम को डिस्क्राइब करना है, then you need a Hilbert space. You don't need a variable x, you don't need a wave, you need a Hilbert space. That's what it says.
okay.
और कुछ नहीं चाहिए हमें, हमें हिल्बर्ट स्पेस चाहिए, और हिल्बर्ट स्पेस के अलावा कुछ और नहीं हम कर सकते।
Okay.
Anything you do apart from Hilbert space, that will be changing the quantum mechanics completely. So any system you pick, you need a Hilbert space for it to describe it. यही मैंने जो स्टार्ट लिया था ना कि हमारे पास दो फ्रेमवर्क्स थे। एक फ्रेमवर्क ये था कि आप एक वेरिएबल ले लें, उस वेरिएबल के लिए आप डिफरेंशियल इक्वेशन लिखें, ये था पार्टिकल फ्रेमवर्क। एक फ्रेमवर्क ये था कि आप एक फंक्शन ले लें, उसके लिए आप पार्शियल डिफरेंशियल इक्वेशन लिखें, ये था वेव फ्रेमवर्क। क्वांटम फ्रेमवर्क कहता है ये दोनों काम छोड़ें, आप एक हिल्बर्ट स्पेस लें, और यूजुअली एक इनफाइनाइट डिमेंशनल हिल्बर्ट स्पेस लें। अब उससे आपने सिस्टम के बारे में कैसे इंफॉर्मेशन लेनी है, दैट वी विल मूव। अभी हम पहले ही पोस्टुलेट पे फंसे हुए हैं, विच सेज के अगर आपने क्वांटम सिस्टम की बात भी करनी है तो वो दोनों चीजें छोड़ दें जो क्लासिकल मैकेनिक्स में सीखी थी, ओनली गेट अ हिल्बर्ट स्पेस।
ओके सर।
और रजीनुद्दीन शुजाउद्दीन।
जी सर। सर ये ऑर्थोनॉर्मलिटी की मतलब हम जो ले रहे हैं कंडीशन, जो हम तो कहते हैं कि वो जो लेंथ है उसको हमें बंद करना होता है ना, तो फिजिकली इंटरप्रिटेशन क्या है यहाँ पर? मतलब ऑर्थोनॉर्मलिटी अगर ना हो तो ब्रेक।
These are not physically anything. ये जो मैं ये लिख रहा हूँ ना, ये बेसिस, ये फिजिकली किसी चीज की लेंथ नहीं है, इज जस्ट अ नंबर। और ये नंबर अगर आपके पास 5 आ रहा है तो, और ये आएगा पॉजिटिव नंबर आएगा क्योंकि ये सेम मैंने लिया है ना, तो बस ये कह रहा है कि आप इसको दोनों इस वेक्टर को 1/5 से डिवाइड कर दें तो ये बस 1 हो जाएगा। सो इट्स जस्ट काइंड ऑफ एब्स्ट्रैक्ट थिंग, किसी चीज की लेंथ नहीं है ये।
ओके।
तमनीन।
जी सर।
क्वेश्चन?
सर कुछ भी नहीं है दिमाग में। आई वाज जस्ट आस्किंग कि अगर हमारे पास, जैसे आपने कहा हिल्बर्ट स्पेस इज अ लीनियर स्पेस, तो अगर हम नॉन लीनियर स्पेस चीज को डिफाइन करना चाहें यूजिंग क्वांटम मैकेनिक्स, सो वी हैव टू कन्वर्ट दैट इनटू द फॉर्म ऑफ
नॉन
लीनियर
लीनियर
स्पेस।
चीज से अभी क्या मुराद है?
मतलब अगर कोई जैसे हमने जीआर पढ़ा था दैट ऑल द थिंग्स आर नॉट लाइक लीनियर में नहीं डिफाइन।
ठीक है। हाँ तो द थिंग इज, आई गॉट योर क्वेश्चन। आपने अक्सर सुनते हैं कि ये नॉन लीनियर सिस्टम है, ये फलाना सिस्टम है, ये सिस्टम लीनियर नहीं है। वो दूसरे कॉन्टेक्स्ट में बात होती है, आप कोई भी सिस्टम ले लें, नॉन लीनियर भी हो, वो जो क्लासिकल सेंस में जो नॉन लीनियर हो, उसको आपने डिस्क्राइब लीनियर स्पेस से ही करना। उसको जब क्वांटम मैकेनिकल डिस्क्रिप्शन करेंगे, इट विल ऑलवेज बी लीनियर स्पेस, इट विल ऑलवेज बी हिल्बर्ट स्पेस, एंड हिल्बर्ट स्पेस इज लीनियर। People have tried to change the quantum mechanics because there are some problems with quantum mechanics interpretational, which we will discuss later. People have tried to change the quantum mechanics by considering non-linear spaces, but none of that works. So far we are stuck only with linear spaces. Even if you are describing a non-linear system like a gravitational field, which is non-linear, or ग्रेविटेशनल फील्ड का तो अभी हमें पता नहीं कि क्वांटाइज सही तरह कैसे करना है, लेकिन हमने फॉर एग्जांपल वी हैव क्वांटाइज्ड प्रॉपर्ली लाइक क्वार्क फील्ड्स, दे आर डिस्क्राइब्ड बाय अ नॉन लीनियर थ्योरी, नॉन लीनियर क्लासिकल सिस्टम विद देन यू क्वांटाइज सिस्टम नॉन लीनियर, मगर क्वांटम डिस्क्रिप्शन, फॉर क्वांटम डिस्क्रिप्शन यू स्टिल नीड अ हिल्बर्ट स्पेस व्हिच इज लीनियर। सो आई थिंक इट वाज अ वेरी इंपॉर्टेंट एंड नाइस क्वेश्चन। Now, let me move to the next topic. So, I have somewhat described the first postulate. I'll probably keep saying things about it as we move on. Let me go to the postulate 2. And the way they start are like kind of ambiguous. Like I said, that you associate a vector. What does associate mean? It's just that it exists for a system. Similarly, next is for each observable. Or to each observable is associated a Hermitian operator acting in the Hilbert space of the system. What is an observable? Observable is anything you measure. It's just a fancy word for anything you can measure. For example, you say, I have an electron, I want to measure its position. I want to measure its spin. I want to measure its velocity. I want to measure its momentum. Anything you want to know. I want to measure its color. Well, color is not a fundamental property of electron, but anything you can think of, like color of a football. As long as it's something which you're gonna measure, which can be measured or observed. To describe it, you will need a Hermitian operator acting in the Hilbert space. Now, let me just ask a question. How many of you have, I don't know how much time I'm wasting on it. How many of you have studied complex linear spaces?
I do.
Can people raise their hands who have done it? Oh, I see it. Yeah. I see just one raised hand and someone spoke up. So I'm just asking how many have. So only 2 people have? If someone else has, just say it now. So I guess, well, I haven't. I'm asking who has. Can those people? Okay. So most of the people go to land. Have you studied?
No, sir.
Okay. So then I think it's worthwhile spending some time, and also because I was of the idea probably people have studied it. So I was like a little bit way too fast. So I'll give some homeworks, and probably in the next class, which is on Saturday, I'll do some problems as well. So then let me then define what's a Hermitian operator. So, but I'm assuming this much. I'm assuming because you are all masters and PhD students of mathematics that you have studied at least the usual linear algebra on the reals. तो आपको at least ये पता कि vectors क्या है और vectors पे operators क्या होते हैं, linear operators क्या होते हैं. So just a reminder, linear operator. Whenever I'll say operator, I'll mean a linear operator. So everything is linear in this theory. So what's the operator? So operator is just a map, a linear map from Hilbert space to itself. That's all it is. So all you want is that if you have a thing like that, an this is an operator, then this should give you this thing. Now, this is a linear operator, and when is this a Hermitian? First of all, let me describe, this is the definition. Hermitian conjugate. So if you have for an operator A, another operator B, such that for all vectors in your space, this is true, that if you act with A on psi and take a scalar product with phi, then this should give you same as, so you just want to change the position of the operator. From acting on the first, you want to translate to, transpose it to acting on the, over here is acting on the second factor, and you want it to act on the first. So the same operator will usually not do the job. So you will need some other operator, B, and if it exists, well, like we will see that it almost always, well, it always exists, then B is Hermitian conjugate of A. And you denote it by B is equal to A dagger. This dagger is a symbol for Hermitian conjugation. And instead of writing this as A and B, usually you write it this way. So you just directly write A dagger. If this is true, then you can bring it to the other factor by writing it as A dagger. Now, if B, you can show that if B is equal to A dagger, that means if B is Hermitian conjugate of A, then A is Hermitian conjugate of B. Right? So B dagger is A. In other words, if you take dagger twice, that's A itself. Well, very easy to see this. You have this property of the dagger. If B is the Hermitian conjugate, you have this relation. Now let's just flip these positions. If I flip these positions, the first postulate of complex linear space was that unlike the real spaces where you can just freely flip in the scalar product, if you flip, you have to put a star. But now I can just take the star of the both things, and then it's saying here B is acting on the first, And here B is acting on the second, and now A is acting on the first. And that's the very definition that A is equal to B dagger, which we have proved. So dagger of a dagger is the operator itself. Now you can see, well, let's discuss the following. If you have an operator A, I haven't really defined what's Hermitian. Let me first define Hermitian, then I'll go towards their presentation in a basis. If A dagger is equal to A, then A is a Hermitian operator. That means for a Hermitian operator, you can freely bring the A to the other side. And if I write this statement in the bracket notation, remember, if I write, suppose right now that A is not Hermitian. Let me, for the Hermitian for now, let me use a different symbol. Let me call it H. So if I take any operator, it acts on the right hand side, but this is not, I should not think of it, I should only think of it as acting over here. It's not acting on the other one. If it has to act on the other side, it has to act as a dagger. It's not the same operator which acts on the other side. This equality holds that if A acts on the right hand side, then on the left hand side, A dagger should act. That's the definition. So this notation is a little bit cumbersome when defining the Hermitian conjugate, because you have to show these arrows. That's why I defined it using the old notation. But if the operator is Hermitian, then because it's in the conjugate of itself, then you can think of it as acting here or acting there. Then you can freely act this operator on either side of this bracket notation. So it's sandwich in here. A normal operator sandwich just means that you have a vector like this, whose scalar part you are taking here. But a Hermitian operator sandwich, you think of it as acting either way. It's really a sandwich. It can act either way you want. Now, let me just discuss this small thing, which I'm sure you know. Matrix elements of an operator. You have an operator acting on psi. This psi, I expand it in a basis. Now, I don't care if it's a infinite basis or finite. For now, I will just write this symbol sigma, but you have to remember sometimes I even use that slightly abused basis of this. So this, for infinite dimensional Hilbert space, sometimes I use this X basis, which is kind of continuous. But when I write this sum, I will have these both things in my mind. But for now, I'll just work with the sigma because it's much easier to do it for now. Now, it's a linear operator, so it goes in. these components, which are just numbers, come out, and you have this. Now I take this thing. What is this? We just saw before that if you have a vector phi and I take j, this gives me the jth component of this vector phi. So this guy is nothing except the jth component of this vector, whatever vector you get by acting on a, on psi with a. You have a psi living here, you act with a, you go to something else. A psi, this vector, and this vector's jth component in this basis is this. So you are trying to find the jth component of the vector which you get. You know what is the jth component of vector psi. Vector psi, you know, its components are known. It's a known vector, so its components which are written over here are known, and you now want to know the components of the vector which you get when you act with A. So now I have used linearity, and now then I just use, I have multiplied with J, with this. Now this thing is defined as AJI, and these are called the matrix elements of A in this basis, because it gives me two indices, so I can build a matrix out of it given the basis, and these are called the matrix elements. But you can see now I can write this thing with this guy like this. So now if these are matrix elements, if I build a matrix out of it, so what I have over here, I have this column, and I'm picking its jth component, this column. I'm picking its jth component by acting with this matrix of A on the vector of psi. So you can always, I think you have all done it in linear algebra. If I have a vector, I can describe the action of linear operators on it to a matrix. And if I want to get the action of two operators, I can get it by computing, by finding the matrix of this. The matrix of this product is, well, this is a very nice technique. I should discuss this technique separately. What I want to do is I want to compute the matrix elements of this operator, identity. What does it do to I, to any basis vector? It does nothing. It does nothing to any vector. But you need the action, to define the action of any operator, you need only its action on the basis. The rest is followed through linearity. So it leaves every vector as it is. So it leaves the basis as it is. So what are its matrix elements? Delta Ji. So I can also describe, this is a very nice idea. I can also describe the right the operators as A, I, J. So it will involve a little bit algebra. I think I should just stop here because we are just running out of time, and this is a kind of an important algebra. We should do it next time. That means Saturday.